студент Сколковского института наук и технологий, и он нам интересен с этой точки зрения. Но прежде всего он нам интересен с той точки зрения, что он является ведущим ученым в области вопросов математики, механики, связанных с космическими полетами. И профессор Кроули сегодня прочитает лекцию, которая называется «Пилотируемая космонавтика в США. Прошлое, настоящее и будущее». Я два слова скажу о биографии профессора Кроули. Профессор Кроули закончил Массачусетский технологический институт в 1981 году. И его исследования, ранние исследования, были сконцентрированы в области динамики конструкции аэроупругости. Он много работал в области математики и механики, связанных с космическими полетами. С 2003 и по 2006 год он занимал позицию исполнительного директора совместного института Кембридж-MIT. Это вот, совместный институт того же типа, как создается Сколковский сейчас институт, тоже совместный между российскими партнерами и MIT. С 1996 по 2003 год доктор Кроули занимал позицию декана факультета аэронавтики и астронавтики в MIT. И провел большую работу по реорганизации этого факультета. Значит, доктору Кроули были присуждены многочисленные награды в сфере образования. Он был избран действительным членом научного общества Маквикера в MIT, участвовал в создании Международного космического университета в Страсбурге, является директором основания программы дизайна управления системами. В общем, если перечислять список всех заслуг, вот число тех, например, журналов, в которых он состоит членом этой коллегии, то это будет очень долгий перечень. Профессор Кроули владеет русским языком, но сегодняшнюю лекцию он все-таки прочитает на английском языке. Те, кому нужен перевод, вы можете взять наушники, там они находятся у входа в этот зал, будет обеспечен синхронный перевод. Виктор Антонович Садовничий до нашей лекции он встречался с профессором Кроули. Мы договорились о тесном сотрудничестве между Московским университетом и создаваемым Сколковским институтом науки и технологий. К сожалению, Виктор Антонович хотел участвовать в этой встрече, но, к сожалению, его сейчас срочно вызвали там, в связи с подготовкой одного высокого визита в Академию наук, и он не смог быть. Но я могу сказать, что вот по той беседе, которая состоялась, мы действительно в дальнейшем будем сотрудничать с Сколковским институтом науки и технологий. И я думаю, что не ошибусь, если скажу, что профессор Кроули будет частым гостем Московского университета. А сейчас я хотел бы пригласить профессора Кроули прочитать лекцию «Пилотируемая космонавтика в США. Прошлое, настоящее и будущее». Профессор Кроули.
Уважаемые коллеги, профессора, аспиранты, студенты, спасибо сегодня за приглашение здесь в Москве. Я просто так, как я сказал, я выступаю сегодня о космических исследованиях космоса. The report I will give today is the result of a commission of President Obama in 2009, the year after his election, when he sought to set a new direction for the U.S. space policy, the U.S. plan for the exploration of space. So he invited, as would any president, a commission of scholars and engineers and leaders of the space program to meet over 4 or 5 months and to produce this report, which is commonly in the US called the Augustine Commission Report, because the chairman of this was Norman Augustine, who was the former chief executive officer of Martin Marietta, an American space company. So we thought it was very important to start this discussion with the question of why we explore. Space exploration came to us as a result of the tension between the Soviet Union and the United States, the race in space in the 60s and 70s, when it played an important and somewhat constructive role in international relations. But since that time, governments have sought to explain to themselves and to their people the important role of space exploration, particularly with humans. So we decided to start with these reasons why we explore. The more tangible, the more concrete reasons is, of course, to prepare for further exploration, to provide support and involvement of science, to develop technology both in space and on Earth, and for economic development and the development of industrial capability. But there are also less tangible benefits that it provides the nations that explore in space an appearance, a practice of leadership in international ventures, that it engages the public, and in particular engages the youth in choosing to study science and mathematics in their school years and in university. So we decided that we would create this set of goals, this set of vision for our space program, the US space program, which is that we go into space not just to stay in orbit around the Earth, but to leave the cradle of the Earth and go truly out into space. You may know that American astronauts, Europeans, Japanese, Russian cosmonauts now travel back and forth to the International Space Station. But the International Space Station, when it passes over the region of Moscow, is actually closer than St. Petersburg. That it's actually only a few hundred kilometers away. So although we go into space, we only go the first few hundred kilometers into space. And since 1972, no human being has been more than 500 kilometers away from the surface of the Earth. So we propose to actually go into space, to leave the vicinity of the Earth and begin exploring. So we say we explore to chart a path for human expansion into the solar system. That it's desirable to start to learn how to work and live on planets past the Earth. And that the ultimate destination of this path should be Mars. Because Mars both has the closest conditions to Earth to live in and work in. It has resources for fuels and oxygen. And it's scientifically the most interesting of the planets because it had the best probability of the beginning of development of life outside of the Earth in our solar system. And that this ultimate goal should actually be to stay on Mars and to work and live on Mars. But this is a plan of 50 or 100 years, so that it's the time to start to begin this program. So I should mention that in the directive to this commission from the American President, Obama, we were specifically told not to consider international ventures. That was a matter of international policy, which the White House will do. But we tried to create in this policy the framework which would strongly indicate that this was not really a policy of the US government, that this was a policy of the US government, but an opportunity in which to build true partnerships with all of the nations that explore space. So we created a set of conditions, of criteria, requirements, against which we would judge our programs, our proposals. So you can see them here, that we should prepare for exploration, that we should develop technology, that we should develop scientific knowledge, expand human civilization, engage the government, expand the economy, and be the basis of global partnerships. These are not charts that I prepared for today. This is actually a chart that I prepared 3 years ago for presentation in the White House. So these are the very words that we used. And the section in the middle indicates that these goals are long-term goals of American space policy from the very beginning of NASA in 1957 to the current time. We started with these goals because we didn't want to propose a program that was just good for engineering, or just good for science, or just good for industry, but to propose a program that all Americans and all American political parties could support, because this has to be a long-term, stable program. Likewise, we create evaluation measures about cost, about programmatic risk, about safety, about the impact on the workforce, the workers, about the sustainability over 20 or 30 years of this program. That these two are important attributes in order to have a long-term space program. So we decided to frame the discussion of the space policy into 5, really 6 or 7 questions. And we proposed alternatives to each of these questions. And I'll speak today about 2 or 3 of them and just very briefly mention the others. The first question was, what is the plan for the US space shuttle? And we confirmed that the space shuttle program had largely achieved its goals and should be ended. There are actually many in the United States and the world who think the entire US space program was ended, but it was in fact just the shuttle program. The shuttle was a great vision and provided great service, but as we now go to explore beyond Earth, we actually need more capability to launch mass into space. The future of the International Space Station was in doubt. That the plans of the partners for the space station, the US, the Russian Federation, the European Space Agency, the Canadian Space Agency, Japan, only went until 2015. And if there was not a plan to extend the space station beyond 2015, we would already begin turning it off. This space station that we just finished building. So we very strongly asserted, with the support, by the way, of Roscosmos, that we should make an indefinite plan for extending the space station as the basis of further partnership for exploration. Then we discussed in great detail, and I will explain to you today, the 2 questions in red. What's the strategy for exploration beyond low Earth orbit? And how should the crew, the people, be carried to low Earth orbit, to LEO, low Earth orbit? So this is actually, I think, the most important figure in the report. So let me explain it. You start in the upper left, which was the starting point of our discussion over the summer, over this 4-month period. And we had before us the question of, what do we do with the International Space Station? Do we go to the moon as the next objective? Do we go to Mars as the next objective? Or do we follow what we called in the report this flexible path, where we defer the decisions about exactly where and when to go into the future while building the capability to do these missions? So the first decision, as I already mentioned, was to decide that the International Space Station, MKS, was an important, a critical part of any of these plans. And that the space station should be used not only for experiments in low Earth orbit, but as a way to prepare us to leave Earth by developing new technologies, by understanding how to work and build larger spacecraft that will be necessary to leave Earth. So the first decision we made was to put the ISS on the path to exploring space. There were many who wanted to close the space station in order to go and take the next step, but we said that's not the right direction. The next decision we made was that Mars is not the next place to go. That going to Mars, which requires 900 days away from Earth, which requires going to another planetary surface and living there for almost 300 days, that this is too big a step. So Mars moves from being the immediate objective to being the ultimate objective. So now the question is, if we finish our work or continue our work on the ISS, should we go to the moon on the way to Mars? Or should we go through this flexible path, which includes places such as asteroids and orbiting planets? So to understand the next step, you have to imagine that in 2030 or 2040, you were the president of the Russian Federation. Maybe someone in this room will. I hope someone in this room will. And the space planners come to you and say, Господин President, we have spent 20 years going to the moon, and now it's time to go to Mars. But in going to the moon, we've never been more than 3.5 days away from Earth. Are you ready to approve a plan to send Russian cosmonauts into space for 900 days? I think most future presidents of the Russian Federation would say the answer to this question is no. We need more experience. So you don't go to the moon on the way to Mars only. Now, maybe someone in this room will be the President of the United States in 2030 or 2040. There's maybe a few candidates. And imagine going to the President of the United States in 2030 or 2040 and saying, Mr. President, we spent 20 years learning to work in space, visiting asteroids, orbiting Mars. But no human has landed on any other planet since 1972. 60 years ago. Are you ready to send American astronauts to the surface of Mars? Probably no. So what we concluded is that on the way to Mars, you would have to do both of these things. You would have to both go and learn how to land on a planetary surface like the moon, and go and learn how to fly far away from Earth into space. So we decided that this is the real option, that we start with the International Space Station, and ultimately we go to Mars. And on the way, we either go to the moon and then into deep space, or we go into deep space and then to the moon. And I'll explain which one we chose later. But the important point is, this is the ultimate objective. And on the way, you have to do both of these experiences. So one of the decisions, decision 5, as it was reported in the report, is what is the strategy for the exploration of LEO? And the answer was, we go to Mars, but with some test flights to the moon. I'm sorry, that one was excluded. We either go to the moon first or the flexible path first. And I'll explain that. Now, if you don't go to the moon as the next objective, where would you go? So it turns out that there are a series of destinations that go through what we'll call the flexible path, and then the moon, and then Mars, which are progressively more difficult. That is to say, they require more and more energy and more time away from Earth. So this scale on the bottom is a measure of the energy beyond low Earth orbit in kilometers per second of velocity change. So you see that without landing on a planetary surface, we can go to the Lagrange points, to the points around Earth and Moon, which have neutral gravity. We can go to lunar orbit. We can go to the Lagrange points of the Earth and the Sun. And then, most interestingly, we can go to asteroids, particularly Earth-crossing asteroids, and we can go and fly by the Moon. Not land, not even go into orbit, but fly by. This would be about a 300-day trip. And it actually takes less energy to fly by the Moon than it does to go to the surface, to fly by Mars, I'm sorry. It takes less energy to fly by Mars than it does to go to the surface of the Moon. Because the Moon is a significant gravity well. So you have to go down propulsively into the gravity well, and then come back up out of the gravity well. So then you could start to go to moons of Mars, Phobos and Deimos, and then finally to the surface of the moon, surface of Mars. So there's a natural progression of these things. So the goal, we said, is to expand beyond the Earth-Moon system as quickly as possible, traveling to many places in the inner solar system. Meeting with planets, and meeting with small bodies, asteroids and comets, but not actually going to the surface of the large bodies, not descending to the surface. And for the larger bodies, the crew, like say Mars, the crew arrives and it conducts automatic probes. It sends automatic probes to the planets, to the surface. So this is really a new strategy for exploring space. That it isn't essential at first to put a human on the surface. That it's more important to send humans to the vicinity and collect scientific data. So this is just a graphic of the possible places, Mars and so forth. Now of these, unquestionably, besides Mars and Moon, the most interesting are the asteroids, the near-Earth objects, the asteroids that come to the vicinity of the Earth. These are interesting for several reasons. One is, about every 100 million years, one of these hits the Earth. Right? The Cretaceous Tertiary extinction was because of an asteroid striking in the vicinity of Mexico. Killed all the dinosaurs. So it's important for our survival on Earth to understand more about these objects and how one might potentially deflect one or destroy one if it was on a path to Earth. The second is that these asteroids contain much information. There are different types, and the different types of asteroids contain different information about the formulation of the solar system, planetary formulation. And third, from a technological perspective, these asteroids are full of useful materials, and that the change in energy necessary to deflect an asteroid so that it could be mined of materials is much smaller than the energy that would be required to lift the material from Earth or from the Moon or from Mars. That this material is almost free in space, almost without cost. Of course, you have to mine and refine it. So there's very significant interest in going to these near-Earth objects or near-Earth asteroids. So what we laid out in this chart is a plan that we would take steps into space of increasingly more and more difficulty. So that the first place to go would be a flyby of the Moon, just basically as a practice flight. And then we would go to the Lagrange point between Earth and Moon, L1. This is an important point because some scientific spacecraft will be located here. And it's a very good place for a operations base if you're going farther out, a way station, a service station, that you really want to get higher to a higher energy orbit than low Earth orbit to do this. Then we would go to an Earth-Sun Lagrange point. And this is where advanced observatories will be located, such as the James Webb Space Telescope. Then we go to near-Earth objects of increasingly more and more duration and energy change. Then to a flyby of Mars, and then to Mars orbit, and then to the moons of Mars, and then eventually to the surface of Mars. And the interesting column here is this one. This is roughly how many days away from Earth the crew, the pilots, the astronauts and cosmonauts would be. How far away. And you see, by putting the events in this sequence, the events are 10 days, 20 days, 30 days, 90 days, 200 days, 400 days, 800 days. So it provides a set of experiments that we can do to make sure that the crew, the cosmonauts, the astronauts, will actually be able to function for this long because of effects of radiation, because of effects of weightlessness, and because of social phenomena. How would it feel to be, as a crew member, 300 days away from Earth, with not much to do for 300 days? What would it do to your mind? We have to make sure that the crew would be healthy, both physically and mentally, when they got to Mars. So this is really, in some sense, the key organizing factor. Because the biggest uncertainty in going to the Moon and Mars is not the rockets. It's not the guidance. It's really the performance of the humans in the system. So this is just a graphic of the options in the flexible path. That you go to lunar orbit, then to these libration points, and then to the asteroids, and then you get to make decisions. Whether you go next to the surface, or you go next to a Mars flyby, or you go to some of these and then the lunar surface. It gives us options for how to deploy these resources in the future. So this was the program for human exploration that was existing when we started. That we go to the International Space Station, we end the shuttle, go to the International Space Station on Russian rockets, and then go to flights again near Earth, and then have a lunar landing around 2030. So this actually didn't allow us to do much other than go to the International Space Station for almost 2 decades. So our proposed plan was actually to continue the International Space Station, but then start going on these trips earlier, and then eventually get to a lunar landing. And one of the important features here is that we were able to identify a means to, we think, save a significant amount of money, which we call the commercial crew capability. But before I get to that, let me explain the question of order or sequence. So everybody says we should go to the moon first, until they calculate the budget. Because to go to the moon, you have to build a capsule which is capable of going to the moon and bringing the cosmonauts back. We estimate that this is an effort of 15 to 20 billion US. That's a billion. And you have to build a big booster, like Energy, Saturn V, but even bigger than Energy and Saturn V. This is 15 or 20 billion US. Then you have to build a lander to go from the surface, from lunar orbit down to the surface and back up. This is at least 20 billion US. And then you need to provide the capability for the humans to work on the surface and move around and explore. And that's another 15 or 20 billion US. So if your first objective is to go to the surface of the moon, you have to do in parallel all 4 of these development programs for a total cost of about $60 billion. And actually, if you go and look at the amount of money that was spent by NASA from 1960 to 1972, and you convert it to current expenses, current dollars, this is just about the amount of money NASA spent. So what's the alternative? The alternative is what we call the flexible path first. So now we can build the capsule and the booster and some small in-space elements and start exploring space first with those for some number of years while you build the capability to have a lander and the surface systems. So this is really just a very pragmatic argument that you have 2 options, and one requires a very high capital expenditure first, and one requires a more distributed capital expenditure. And in this case, it's always better to do the distributed expenditure. So what are the benefits of the flexible path? We would be able to start away from the Earth faster. We'd be able to go to destinations that humans had never visited. We would go to new places each year on the flights and develop the capability to work away from the Earth in deep space. We would be able to bring together the robotic exploration and the human exploration, do some interesting science, have a good expense profile, and engage international partners. So this is the very important point, that we wrote this policy, or we drafted this report, without any specific recommendation of including international partners. But as a practical matter, this program will not be achievable by the United States government alone. That it is absolutely necessary to have a deep and true partnership of the US, of Russia, of Europe, and other spacefaring nations, including perhaps China, in order to achieve this. That this has to be an international effort of high significance, and not just a Russian program or an American program. One of the interesting things that we found as a way to accelerate the program is this idea that we actually move the job of lifting the crew to low Earth orbit away from the government and towards commercial entities, towards companies. That we should make going into space now a business. And it's the timing of the discussion today is actually very, very good. Because in the next week, if all goes well, an American company, SpaceX, will launch the first commercially developed rocket with a capsule called Dragon to the International Space Station. And that this capsule has been designed so that it can be converted in a few years to a human carrying capsule. And just a few months later, a second American company, Orbital Sciences Corporation, will also launch a commercially developed rocket towards the International Space Station for the purposes of delivering cargo. So we will see, actually, in the next few months, the beginning of this era of commercial launch into space, commercial peaceful launch into space, for the purposes of carrying first cargo and then crew. So watch in the next few weeks for these developments. And because of the way such developments work and are funded, we think that there'll be, the committee believe very strongly, that there would be a net savings of money in the near term by allowing the commercial suppliers, the commercial companies to do this. So when we finally put these options together, we had what's called a decision tree, an applied decision analysis. And you can see that there's some decision on the budget, which is the first line. The NASA budget, by the way, is higher than it was several years ago. And then there was options about which pathway to take, the flexible pathway to moon first, and then various launch vehicles, which I didn't discuss today. So when we were completed, when we took the then existing US space program policy and plotted the value that it would create on this so-called radar plot, which is a way of indicating 12 different metrics for the program. Exploration, technology, the ones I mentioned earlier. Science, human civilization, economic expansion, global partnerships, public engagement, schedule, safety, workforce, sustainability, and life cycle cost. You can see that the then current program is shown in the blue trace. And the program that we recommended is shown in the red trace. So in every dimension, the program that we recommended, including global partnerships, in every dimension, the program we proposed had more value, was more desirable than the then existing program. So let me summarize what's happened in the last 2 years. That this report was published, the White House took it as the basis of their budget 2 years ago and changed or chose some things which were not exactly the primary recommendations of our report. There were other options. And the Congress and the President debated this for about a year. Some would say they're still debating it. And I think it's actually quite remarkable that the current status of the policy is almost exactly what was recommended by this commission. That if you read the report carefully, and see what our recommendations were: ending the shuttle, continuing the space station, commercial space launch, going more flexibly forward, developing a heavy booster based on the shuttle technology, you'll actually see that most of the recommendations were approved. So I would conclude with two thoughts. The first is, as I said, that I think it's absolutely essential that we think globally about how to do this program. And we bring ourselves into true partnerships that are long-lasting about how to go into space and explore. I think that's a general political conclusion. But I would, especially for the young people in the room, the students, I would say that there's another lesson that I learned from this committee, this commission, which was something that was taught to me by one of my professors. We were one day at NASA Houston Space Center, and we went into this enormous building. And he showed me this experiment that was going on there. And he said, "Ed, do you recognize this experiment?" I said, "Yeah, I recognize this. There's a very small version of this in your laboratory at MIT." And he said, "Let this be a lesson that you have to be very careful in life about the advice you give to governments, because sometimes they actually listen." So students of MGU, who will be future leaders in Russia, remember that if you give advice to the government, be very careful, because they might actually do what you say. And then you would have this great responsibility for the advice you're giving. So in this experience, I look back and say, there have been many reports written about space policy in the US. But this was a report which actually had some significant influence on the decisions of the government. And I hope, whether President Obama is re-elected or potential President Romney is elected, that this report and this policy are well-based, well-reasoned, and will survive and be continued throughout the next presidential administrations. So thank you very much for your attention today. And I'm more than willing to answer questions, as the prorector said, either on space exploration or if there are a few questions on scope of attack.
Okay, thank you very much, Professor Crowley, for this very interesting and challenging lecture. I'm sure that there are some questions on astronaut problems and questions on Skolkovo attack. Please, who have the question?
Sure.
So I will start with you. Если можно, микрофончик какой-нибудь еще.
Можно?
Да.
Ну, я громко буду.
Тут акустика хорошая.
Okay. I'm head of Lunar and Planetary Department of Sternberg Astronomical Institute. And Skolkovo expert to Space Cluster. My question is, what is communications or relationship between Planetary Resources Incorporation, a private field, and NASA? Thank you.
I'd have to say that there's really very little private interest, commercial interest in planetary resources that I'm aware of. There is, of course, at NASA, at JPL, at Goddard Space Flight Center, and so forth, scientific interest and development interest funded by the government. But there has been, up until this time, as far as I know, not much commercial interest in planetary resources. So I actually have several laws of human spaceflight, that I teach my students. And one law, the first law, is that it's much easier to make money in space by moving photons than molecules. That is to say, the commercial exploitation of space with imaging, with sensing, with optics, with communication connections, is where you put the commercial infrastructure in once, and you have recurring use by moving photons, basically, is a far easier way than by moving mass. So I think that the primary barrier is actually the cost of launch and the cost of recovery. That you would have to have something extremely valuable in space in order to be able to bring it back and have any positive commercial value. So not much development, I think. And the barrier is launch cost.
Yes, please.
We represent Roscosmos, Central Research Institute for Machine Building, located in the city of Korolov, Moscow region. Our questions are the following. Is the ISS in demand among scientific community of the United States? And the next one is, when in your opinion, the ISS program will be actually finished?
So do you want the official answer or the real answer?
The both.
The official answer. The official answer is the ISS is enormous scientific value, and that the current plan is to extend the ISS at least until 2020, at which time there'll be some further decisions. So let me take the second one first. I think the most rational strategy for the ISS was proposed by, I believe, the head of ESA, who said that about every 3 years, we the partners in the ISS, should evaluate the ISS and its effectiveness and its cost and make a decision whether to extend it for another 3 years or not. The issue of what to do with the ISS, the physical thing, when we don't want it anymore, is actually a very complex question, as you know. I mean, there is no rocket engine large enough to produce the delta V, actually the impulse, necessary to deorbit the ISS in one piece. And so we would have to somehow disassemble it. It's like running a nuclear reactor. It's actually easier to keep running than it is to take it apart for a variety of reasons. So I think that when people start considering the value and the cost of continuing to operate the ISS versus the cost of stopping to operate the ISS, which will be billions of dollars to stop running the ISS, then it will tend to prolong the life considerably. Now, let me tell you the real answer. The real answer is, I believe that what will probably end the life of the ISS is a mechanical failure. I think that something which is large enough so that it cannot be repaired will fail. The bearings on the solar panels, the solar batteries, the control moment gyros, and that will then that will cause people, that type of failure will cause people to say, maybe it's time to start thinking about the end of the ISS. Because we don't, without the shuttle, and until another large booster is built, have the capability to bring up a large piece. Even Proton, well, Proton would be the best we have. Now, as to the scientific capability, I was also on the presidential commission of President Clinton in 1993, one of the outcomes of which was to recommend the combination of the space station programs of the US and the Russian Federation, which of course happened. And at that time, we calculated the expense of filling up all of the racks on the space station with scientific experiments. And there were, I can't remember, 40 or 50 full space station racks at the time in the plant. And it would cost billions and billions and billions of dollars to fill these racks with experiments. Nobody had that budget. They had the budget to build the facility, but they didn't have the budget to put the experiments on. So we argued at that time that the amount of money that was budgeted, that was planned for scientific exploration,